And to begin with, I want to kind of show you what the problem is saying on this. This is another problem that's like example 2. It has to do with perimeter and area. There's just a little difference between this. So what this problem is saying is you're building a fence, and it's got 3 sides this time, and it's built next to a river, so you're not going to do a fence on the river. That kind of is like a border. This is just another kind of practice problem to get you the hang of this. So you have a rectangle. And then it also says that you have this much fence, so that's a condition or a constraint on the problem. However you build this, you're going to have 96 feet of fence. And then what you're going to try to do is find the maximum enclosed area and the dimensions that make that a maximum. So when I put these diagrams on here, I'm trying to show you different ways you could build this. Here's your river. Here's your 3 sides of fence. That's your area. Here's another way. Make it real long and skinny, okay? So you could still have these 3 numbers there are going to always add up to 96, right? Another way would make it long and skinny this way. Now, if you look at those 3 diagrams, which of those 3 looks like to you it has the most area? Probably the first one, okay? I just tried to stretch this out on my computer, but that's the idea. So we've got to figure out what that is. So to me, it's pretty logical. Making it long and skinny, you're not going to be able to put much in there. But if it's more like that, you'll probably have a lot of area to enclose them. So what you got to do on these problems is the first thing that you always want to do is you want to kind of set up equations when you're doing that. You draw a picture. I've already got a picture. Okay, now let's go ahead and let's use this picture to kind of show us this. So I've already just labeled the sides x and y. 2 of the sides are equal, and then we have that. So what's the problem say about these numbers? They add up to 96, exactly. That's what it says. It says you have 96 feet of fence. So what you would get is you would get this equation. You would get x plus y, that's the perimeter. That's equal to 96. That's an equation. Now you got like terms, so you can put that together. You would have 2x plus y is equal to 96 like that. Okay, so that is an equation that we have. Okay, you always got to look at what equation. Now the next thing that's real important is now you got to kind of begin to think about what are we going to take a derivative of, and that's what we're working with. Well, what it says is it says you're maximizing the area. So that means since you're maximizing area, you've got to find a function for area in one variable that you're going to take a derivative of. Okay, so let me ask you this question. Tell me how you would find the area of this figure. You do x times y, right? Okay, base times height. So that's just going to be x times y. So right now, see, that has 2 variables. You don't want it to have 2 variables. You want it to have 1 variable, and that's the key. So what you got to do is work with this equation and just solve it for either variable. I'm just going to solve it for y because it's easier. So what I'm going to have you do is just write down y. You got 96. You subtract 2x from both sides, or you can just move that to get minus 2x like that. Okay? Now what do you think you do with that?
Plug it in.
Plug it in the other one. Exactly. Good. So this thing right here, that's what y is, so that's going to plug in there, see? So you always want to get your function down to 1 variable. Otherwise, you aren't going to be successful with getting it figured out. So I'm going to call this a then, and I've got x, I leave alone, and then change that y to 96 minus 2x. I'm going to write that as a of x. It's a function of 1 variable x, and you could have solved that equation right there for x and plugged it in. You'd still get the same answer. It would just be in terms of a different variable. So let's go ahead and just multiply this out. So that's a of x equals 96x minus 2x to the second. Okay, so see, that's the key to the problem, is getting down to a point where you're ready to do the calculus. Okay, you guys with me so far? Okay, so now what we're going to do is we're going to kind of look at the conditions of this problem and everything too. There's a couple of things that you always want to look at in here. There's conditions built into the problem. First of all, x has to be greater than 0, right? And really it has to be strictly greater than 0, not greater than or equal, because, and why is that, by the way? No, because it's a piece of fence.
Positive,
Okay, fence has to be positive. Okay, and also y also has to be greater than 0 because it's a piece of fence. Okay, and then the other thing is these things also have to be less than 96. So you would have to you would end up having that this thing 2x plus y, that whole thing right there would have to be less than 96. Okay, you don't really have to worry about that too much in this problem because the mathematics is going to work out. Once we do our derivative and look at our function, you'll kind of see how that goes. And that's less than 96, and it's really less than, or, hold on, that's not right. I wrote the wrong thing on that. Okay, the idea on that's going to be is all of the individual pieces have got to be less than 96. So all I'm going to do is just write those two things like that. Okay, now in step 4, we're going to go ahead and do our derivative. So now we want to find what maximizes that area. So what's the derivative of your function for area?
96 minus 4x.
Okay, 96 minus 4x. What do you do with that?
Set it equal to
Set
0.
it equal to 0, exactly. Okay, just kind of doing critical numbers now. So you want to write 96 minus 4x equals 0. Okay, solve that equation. So you can move the 4x the other side to get 9x equals 4x. Okay, and then divide by 4. You can take your calculator if you need to, and that'll give you a whatever your critical number is then. So I'm just going to do 96 divided by 4, and that will give 24 then. Okay, so we have x is 24. All right. Now we also got to find y. That's what x is. So where do you go to find y? Well, the easiest place is right here. Okay, that equation right there was already solved for y. So it's logical to just plug the 24 into this function to get that. So basically we have x is 24 now. Now we're going to have y equals, and let's see, on this I'm going to have 96 minus 2x. Just plug in the 24. Work out your calculator on that. So I'm just going to do 96 minus 2 times 24 is 48. So that's also 48. Okay, so you get, your dimensions are going to end up being 48, and that's what y is, and then 24 is what x is. And I guess that's in feet like that then. Okay, so that's how you maximize this. Now I'm not done with the problem. I want to show you a few other things with this. So does that make sense what I've done so far? Okay, now I want to show you something. I haven't emphasized this very much, but on step 5, what I want to do is I want to show you how to verify that this is a max. Okay, what I've had you do before is do sign charts. Okay, and just what you would see is you would see that the function's increasing then decreasing. There's another way to tell that you can verify that x equals 24 is a max. So let me show you how to do this. What we do is what we call the second derivative test. I'm going to do this on a lot of these problems, and this is a real quick, efficient way to tell whether you have found the maximum or not. Okay, so what we're going to do is the first derivative. Let's just write down the first derivative. That was 96 minus 4x. Okay, now tell me what the second derivative is. Okay, it's negative 4. Okay, now go back to your little concavity pictures, the faces I taught you. This is an easy way to remember it. Okay, you got a negative number for the second derivative. What does that mean? It means you're concave down, and this is a visual more than anything. That just helps you see that that's a max. Okay, that's because the top of the frown is a max. Okay, that's just a way to remember that though. Okay, so if you ended up with a positive on the second derivative, then you'd have a minimum. So if you want to verify it's a minimum, that's what you do. You don't have to do the sign chart. Okay, to me it's a lot faster most of the time to verify that way. Okay, so anyway, here's what we get on the problem. So let's just draw a picture of what we found. We found basically this. Here's your river, and we found that x was 24 feet here, and 24 feet here, and then what was it? 48 feet, like that. Okay, so that's what we found. So how would you find the area? Just multiply them together. So, okay, so the maximum area, all we need to do on that is just area is going to be 48 feet times 24 feet. You can do that on your calculator, and that will tell you what that maximum area is then, okay? And what are the units going to be? Square feet, right. Feet times feet is feet to the second power, so that's going to be square feet. Okay, so it looks like the answer to the problem is 1,152 square feet. The dimensions, you can just say 48 by 24, like that, and then that problem's solved. Okay, that's it. Okay, so the hardest part of this problem for most students is this, is getting down to this point right here where you have a function you're ready to do a derivative on. You're going to find most of these problems that you're going to do, the derivatives are going to be easy. They're going to be complicated things with quotient rules. They're going to be polynomials most of the time. So if you can get that done, then you're probably going to do fine. That's the hardest part. Does that make sense to everybody? Okay, all right. Okay, so the other thing that I want to remind you that you can do, you don't need to do this right now, but another good way to look at this is if you just graph the function you did the derivative with. If you do 96x minus 2x to the second, now you would have to work with the window on this. The window, what I'm going to do is I'm going to go from 0 to 96. The reason I'm doing that is because that's a condition in the problem. That's got to be smaller than 96. And then our area was 1152. So if I just did something like this and made that y max like 1200 or something like this, okay, you don't need to do this. I just want to show you what happens, okay? Whoa, did I put the wrong thing in? Yeah, I didn't even put my function in, okay? So you need to put in 96x and then minus 2x to the second. This is a good way to kind of visually tell what's going on in the problem anyway, all right? So that's your function, okay? It has a maximum, doesn't it? So if you trace at 24, notice that verifies it right there. So you can do that too. All right, does that make sense? Okay, so you can always graph the function that you did the derivative of to take a look at it and see if you're on the right track, okay? Okay, next problem. This is another problem that's kind of an interesting one. And this is kind of something that, you know, you do in industry. You know, we talked about how you can make a container maximize how much it carries. It maximizes volume. So what this problem is saying is it's saying that you have a box and it doesn't have a top, and you build it by taking a sheet of cardboard that's 12 by 16. And what you do is you cut out the squares and you make a box. So the first thing that you want to do is visualize what's going on in this problem. Okay, the idea, I'm going to have you label a couple of things on this. What this problem says is it says you're starting off with a piece of cardboard. Go ahead and draw this on your paper. That is 16 inches. And then this piece right here is going to be by 12 inches. So what you're doing is you're making it into a box. Well, the way you make it into a box is you just cut out rectangles of the same size and then you fold. Okay, can you guys visualize that in your head? So if you just take those out and fold the flaps up, you're going to have a box that looks like that. So these are different ways to make it. You could cut out little tiny squares. If you did that, you would have a very small flat box that probably wouldn't hold much, right? You could make squares like that. Looks like that holds a little more. You could make the squares bigger, it makes that. But if you make the squares too big, then you don't have a box anymore, okay? Because it's actually going to get bigger for a while, then it's going to start diminishing. Does that make sense? Okay, so again, what we got to do is we got to set up the equation on this. So the key thing we're going to do is the variable is this, okay? X is what is the size of the square we're cutting off. Now these are supposed to be squares. So just kind of label those like this, and then we're maximizing volume, okay? All right, so we're going to maximize the volume. All right, so I need to ask you this and see if you know how to do this. Okay, how do you find a volume of a box? It has to do with three things. Okay, what does a box have? It has a length, it has a width, and it has a height, right? So write that on your paper. Let's just write that as length times width times height. So we got to take this diagram and write a function out of that, okay? Well, here's the way this is going to look, okay? The length of this thing is not 16. It starts 16, but then what happens? you cut out 2 x's. So what would this be?
16 minus 2.
Good, 16 minus 2x. So you start with 16 and you chop off the 2 x's. So you probably want to label on here something like this. That right there is 16 minus 2x. Okay, so that's what the length is that 16 minus 2x. Okay? All right, the width. Okay, it's not 12. What is it?
12 minus 2.
It's 12 minus 2x. Okay, does everybody understand that? That's key. Okay, so that's going to be 12 minus 2x. So that's your width. Okay, now what's the height? Remember, you're folding it up. So how tall, imagine folding that flap up. How tall is that going to be? X, good. Okay, so you're going to have X. So that's what you have. Okay, so your dimensions after you cut out the squares are 16 minus 2x, 12 minus 2x, and x high. Does that make sense? That's the first thing. Now notice that function already has one variable in it. Okay, so we don't have to worry about that. So what we're going to do is, that's really the first step, is kind of getting a picture. Second step's getting your equation built. And this is your function. So I'm just going to write this as v of x is equal to, and let's write it like this, okay, before we do anything with it. So let's just write that as x times 16 minus 2x, and then 12 minus 2x. So that's the function we're going to maximize. Okay, so what are you going to do? Take the derivative and do what with it? Set it equal to 0. Okay, do that. Okay, now, if you're going to do that derivative, the best way to do that is not a product rule. Just multiply it all out. Okay, so that's what I'm going to do. It's much easier to do it that way. Product rule would be kind of, it'd work, but it's just kind of a waste of your time. So what I'm going to do is I'm going to choose to do it this way. You could either multiply the x through the first thing and then FOIL, or you can FOIL and then multiply by x. I'm going to do it like this. So let's see. I'm going to go ahead and just go ahead and start doing your FOIL here. So let's see, we would have, might need to use my calculator. You might get into some pretty big numbers on this. So 16 times 12 is going to be 192. Okay, and then the outside term is going to be minus 32x. The inside term is going to be minus 24x. And then the last term is going to be plus 4x to the second. Okay, like that. So I've got that. Okay, now I'm going to just keep kind of working with this. So I'm going to collect like terms. That's 192. And let's see, 32 and 24 would be what? 56x. 4x squared. Now what you want to do now is just distribute the x through that. So you would have v of x is equal to 192x minus 56x to the second, and then plus 4x to the third. Okay, we haven't even done any calculus yet. We're just getting ready to do calculus. Okay, everybody with me? Okay. The reason I'm multiplying it all out is I need to do my derivative. Okay, all right, everybody okay? Okay, so let's go ahead and do the derivative. Okay, so v prime of x is going to be 192. Okay, you're going to have 192 there. You're going to do the power rule there. 2 times 56, I think, is 112x. Okay, then a power rule here is going to be 12x to the second. So we got that. Okay, so that is your derivative. Okay, what do we do with it? Set it equal to 0, exactly. Now, what will happen on this is either it will factor or it won't. If this is a quadratic equation, so if it doesn't factor, you got to go to the quadratic formula, okay, which we may have to do, which is kind of a bummer, but it's not hard, okay. Now, here's what I would do. Before I factor it, do any of these numbers divide by anything? They all divide by 12? They might. Let's find out. I hope they do.
112 doesn't.
The 112 doesn't? How about 6? Let's see if they all divide by 6.
No.
112 by 6, does that work?
No. By 4.
No, that's no good. Let's try 4.
4 works.
112 divided by 4, does that work?
Yep.
And then 192 divided by 4, does that work?
Yep.
Okay, so let's do that then. Okay, it just makes it a little simpler. Okay. All right, so you don't really have to take the common factor out, but you can if you want to. One of the easiest ways to do this is just divide everything by 4, because I suspect we'll have to go the quadratic formula on this, but we may not have to. We're going to find out, okay? So let's see, 192 divided by 4 is 48. And then 112 divided by 4 is 28. And then you have 3x squared like that, okay? And a problem like this, if I don't feel like factoring, I just go ahead and just go to the quadratic formula. So I think I'm going to go ahead and do that. So I'm going to write this as 3x squared minus 28x plus 48. And the quadratic formula will tell you whether it factors or not anyway. So you could go ahead and try to factor that if you wanted, or you can just jump right into the quadratic formula, okay? All right, so let's just go to the quadratic formula. So you have negative b plus or minus square root of b squared minus 4ac all over 2a. Okay, you guys remember how to plug that in from your past? Okay, a is 3, b is negative 28, c is 48. So go ahead and start plugging that in. Use your calculator to help you. So it looks like you'll have negative 28 plus or minus the square root of b squared, and then 4a, which is 3, times c, which is 48. And that's one big fraction bar all over 2a. And a is going to be 3 like that. Okay, let's go ahead and you can get your calculator out and start number crunching. Let's see if I got my regular calculator with me, because when I use that one on the screen, I can hardly see it. And if we end up getting a decimal, we'll just like round it to 1 decimal place or something like that. Okay, so I'm going to go ahead and just kind of finish this like this. So that's going to be 28. And see, you can do what's under the radical in one step. I'm just going to take like parentheses, negative 28 squared minus 4 times 3 times 48. And then that's going to give 208. Okay, that just did on your calculator, and that's 6. So you want to see what the square root of 208 is. I think that's not a perfect square. That's decimals. Okay. So we would have had to have used the quadratic formula anyway. I suspected we were going to have to. All right, so what I'm going to do here is 28. Now I'm going to go ahead and just get this on my calculator. When I do the square root of 208, I got like 14.4, and I'm rounding that. Okay, all right? And then that's over 6. All right, everybody with me there? Quadratic formula, okay? Just you know the formula, know how to plug it in. You're going to use your calculator to help you. Now what we got to do is go in 2 directions with this. So we need to do 28 plus 14.4 over 6. And then we also need to do 28 minus 14.4 over 6 like that, and then get that answer. Okay, one of the answers will make sense, the other one will not, and I'll explain that. So if I do 28 plus 14.4 and then divide that by 6, what I'm getting is about like 7.1 if you do that. Okay, if you do 28 minus 14.4 and then divide by 6, you're going to get about 2.3. I'm getting like 2.26 like that. All right, everybody with me? Okay. Okay, now it's not 2 answers. One of these answers is totally ridiculous. Let's see if you know that. Okay, let's look at the 7. What would happen if this was 7?
You cut out more than half of the box.
That's more than half of 12, right? So it's impossible. Okay, you can't do it. In fact, what if x was 6? Well, you could physically cut out the square, but you know what you'd have? You'd have a piece of paper, and if you folded it, it would have 0 volume, right? Okay, so one of the conditions on the problem, see, is that doesn't make any sense. That should be your answer right there, okay? So the dimensions are going to be, and this was in inches, are just going to be, you would just say 2.3 inches by 2.3 inches, okay? And then I'm going to show you a couple other things to do to finish this up that kind of helps you a little bit. So that would be the way that you get the dimensions that maximize this. Now let's do something on our calculator together on this one, because this is another thing you can do. I didn't ask you for the maximum volume, but I'm going to go ahead and compute that. So if you want to find the maximum volume, what you do is you would take that 2.3 and you'd basically just plug it into your volume function. Or you could graph it and trace it out, which is what I'm going to do. So why don't you just do this along with me. Put in your volume in the factored form. The reason I recommend that is because what if you screwed up with the foiling? Then you're not really checking and verifying anything. So let's just go like this. X parenthesis, then we had what, 12 minus 2x, and then close the parenthesis, then we had 16 minus 2x, like that. So let's get that put in, and then let's kind of talk about what the window is going to be. Well, first of all, here's the thing that's kind of important on this. What is the biggest value that x could be? I already said that a minute ago. This is 12, so what's the biggest possible x? 6. Everybody understand that? Can't be bigger than 6. So what you're going to do is you're going to have, on your x, just go 0 to 6. Okay, because the problem has absolutely no meaning past 6. Scale by 1. The volume, hey, just look at your table of values. I'm just going to go second table. And notice that, well, I'm way up there. I'm way down in the negative numbers and everything. So what are the numbers looking like? Those of you who are with me on the calculator. What's the volume Y values like?
X is 140, then 192, 180.
192. What's the biggest one you see?
192.
Okay, so let's try this then. Okay. All right, so let's go like 0. You said 192 was the biggest, so go do like 250 or something like that. Okay, and then maybe scale by 50. And I'll slide this over here so you can get that put in if you need to. Okay, all right. So now if you graph this, now see this is not a parabola. It's a cubic function. That doesn't look like a parabola. I mean, it's more like a cubic function like that. And notice at 6 you have 0 volume. Does it make sense why you have 0 volume at 6? Because you have a piece of paper. You don't have a box, okay? So now if you just trace at our answer, 2.3, okay, then you can tell, okay, that's a max, okay? And then that volume would be the Y value. So let's also write down that that volume is going to be like 194. Well, let's just round that to well, let's just round it off to 194. That's good enough. Okay, and then that would be in what kind of units? If it's volume. Cubic. Okay, so there you go. Okay, so again, you can use your calculator to help you make sense of the function. So problem solved. Okay, so if you make it, that's the way to make that box so it holds the most amount of material. Okay, that's a practical engineering problem. Okay, all right. So let's move on to the next couple of things. The next couple of things are pretty simple. And I think the last couple of examples are the ones that are kind of tricky. That one's not too bad. I like that problem. That's kind of a good standard one. Okay, so we've been doing this a lot, so hopefully you're getting this down a little better by now. Okay, so you're given a cost function and a price demand function. You're given a domain from 0 to 25,000. And what you're going to do is find the production level that maximizes profit. Now, we've already done this before, but just to review, because this is super important to know how to do, how do you find profit? You do revenue minus cost, exactly. So profit, I'm going to write P of X equals revenue minus cost. Well, I gave you the cost. I didn't give you the revenue. But can you find revenue?
X times P.
X times P, okay? Remember Windows XP? That old operating system? I always think of that when I do this, okay? All right? So the revenue is X times P. So you would just take X times your price demand function. You have a problem like this on your homework. So times that, just multiply that out, okay? So you want to do a distributive property there. So that was going to give R of X equals 14X. And then you're going to have X times X, or X to the second over 4,000 like that. Okay, so that's your revenue. Okay, so since we're maximizing profit, your next move is to go ahead and find your profit. Okay, so you should have been doing this on your assignment that you're doing this week. So the revenue is 14X minus X to the second over 4,000, and your cost is 8,000 plus 5X like that. Okay, so you want to go ahead and simplify that, you know, and you'll probably have a few like terms you can put together. So that's really 14X minus X to the second over 4,000. And be careful here with the minus. You got minus 8,000 minus 5x, right? Be sure that you don't mess up on that because that'll mess up the whole problem. You're just wasting your time if you don't get this part right. Okay, so put your like terms together. I'm going to put it in this order. I'm going to put negative x squared over 4,000. And then 14 minus 5 is what? 9x. Then you got that. Okay, so that's the first part of the problem, is get the function that you're going to do a derivative with. In this case, it's not that hard because it's a formula. You don't have to figure out, like the last problem, we had to know something about volume. Okay, so what do I do with this?
Find the derivative.
Find the derivative, set it to 0, okay, right? And this time I'm also going to show you that second derivative test because I want you to start kind of doing some of that. So let's go ahead and do our derivative. Okay, how do you do the derivative of the first term?
1 over 4,000.
Okay, you got a constant. See, that 1 over 4,000 is a constant. Just write it down. And then the derivative of negative x squared is what? Negative 2x. That's how you do the derivative of that. Then the derivative of 9x is 9, and then the derivative of that is 0. You don't have to put the 0, I'm just emphasizing it. The reason I asked that, several of you were asking me about that on your homework. Malphas, I know you were asking me about that. So the idea with this is that's just a constant, okay? And then you're just doing the derivative of that, okay? Well, sometimes students don't see that the right way. Really, that is just saying negative 1 over 4,000 x squared, okay? That's what it is. That's a constant, so you write it down. Okay, so now you could also simplify this if you want to. You don't have to, but I'm going to go ahead and just reduce that. 2 goes into 2 once. 2 goes into 4,000 2,000 times. Okay, so then I'm going to have p prime of x is equal to, it looks like, negative x over 2,000 plus 9. Okay, now that's what we're going to set equal to 0. We're doing that to find a critical number. Okay, so we want to go ahead now and just let that derivative equal to 0. And then we can solve this equation. Okay, what's the easiest way to solve this equation?
Put 9 over there and times by 2,000.
Let's get, x on one side. To me, the best way is just slide the x to the left. That way it becomes positive and then x is on the left side. Okay, so that's going to give x over 2,000 is equal to 9. And then what?
Times each side by 2,000.
Right, multiply by 2,000 because you're trying to get rid of the fraction. Okay, so we've got x is equal to, and what's that, 18,000. That's what that is. Okay, now we're not done with the problem. We've done the calculus with the derivative. So the production level is x, right? Okay, what that means in this problem, I don't think I said, these are calculators. So what does that 18,000 mean?
You plug that into the P function.
If you want to find the profit, if you want to find the value of the profit. But 18,000, what does that mean?
It's the max production.
That's how many calculators you're making to produce that maximum profit. That's not the maximum profit. But the question says, give the production level. So that's the answer.
Oh, so we're done. Okay.
Right. So the question is not find the profit. Now you could do that certainly by plugging that into the profit function then. Okay. Right, so we would have that. It would just be 18,000 calculators produces maximum profit. Okay. Now, just I'm not going to do anything on the calculator on this, but I want to remind you that you always can. What I want to do on this again is the second derivative test, and what that does is that will verify that that's a maximum. It's a simple way to verify it's a maximum. So let's go ahead and write down the first derivative is negative x over 2,000 plus 9. Now we're going to do the second derivative. Okay, do you know what that is? What'd you say?
Negative 1 over.
Right, it's the number in front of x, right? Not just the negative 1. See, that really is negative 1 over 2,000x plus 9. So the derivative of that is negative 1 over 2,000. Now what matters is that's a negative number. And you can go to this visual just to help you remember. If the second derivative is negative, you are concave down, right? Look at that, okay? It's a max. Okay, that's just a way to remember that. Doesn't really have to do with the concavity. It has to do with the way that looks, okay? So that's what the second derivative test says. If that's a negative, then that's a max. If it was a positive, it'd be a minimum. That's a real fast way to do that. Okay? All right, problem done. All right, so that's not too bad. By now, that ought to be just, you should be just whipping through those kind of problems. So those are important for this class. Okay, next problem, similar. I want to do a couple more things with revenue and average cost of that, and then the last two problems are the ones that are going to be a little harder to explain, I think. So let's see, this problem you've got looks like you have a revenue for zip drives and a cost, which is, and then what you're doing is you're maximizing the profit. So this is almost the same thing. I'm going to go ahead and just let you guys try to do this on your own, but tell me how you would start this. You want to maximize profit, so what do? You've got to find the profit, and how do you do that? Okay, you've already got the revenue, you already got the cost, okay? So I'm going to go ahead and just pause this for a minute and let you guys go ahead and take it.
Do we plug that x value into the derivative? Or
No, into the profit.
Okay.
So the profit function is what you're taking the derivative of. So the first thing is just make sure you got the same profit I got. You got that? Okay. All right. And then I'll do the derivative. That's your first derivative. You getting that? Okay. But if you get the profit function done okay, then it's not hard to finish the problem. Then what?
You do these,
Set it equal to 0. Okay. So you guys get this okay? Okay, what'd you get?
9,000.
Okay. Okay, so I should be able to do this and then divide by 0.04. And let's see, what'd you say? Yeah, 9,000. Okay, so if you got that, you're in good shape. Okay, so that's x equals 9,000, but what does that mean? That's production level. So that would be how many zip drives that you're producing. So then what you want to do is you want to just do the profit at 9,000. So the question is, where do you plug it in? Profit function, right? Plug it in there. Okay, don't plug it into the derivative because that's what you're doing is finding profit. Now you can do this on your calculator, but you would do negative 0.02 times 9,000 to the second. And 360 times 9,000 minus 100,000. And you can just do that on your calculator, and then that would give the answer. Anybody do that?
1,520,000.
Okay, should be a pretty big number.
Why is your 100 being subtracted?
Say it again, I'm sorry.
Why is the 100,000 being subtracted?
So why you distribute the negative?
Oh, that's distributing the negative right here. Because when I'm doing the revenue minus the cost, that minus distributes through. That's, to me, is a real easy mistake to make. You got to be careful. If you don't get that right, it actually wouldn't mess up your answer. I mean, it would mess up the answer to the final part there, but it wouldn't mess up your derivative. Okay, so let's see. So what, I'm getting like 1,520,000. Anybody else get that? Okay, all right. So that is 1,520,000 should be the answer to the problem. Okay, that's it. Now, another thing, just to kind of remind you, on this second derivative test, you don't have to do this, but I just want to remind you that if you take the second derivative, okay, now here's your first derivative. That's what I'm highlighting. So what's the second derivative? It's a negative number, right? Okay, that's what it is. So that means that you have a negative, got a max. You guys see what I'm talking about by that? It's a very fast way to tell that you got a max or min. Okay, and you're going to do this a lot on these problems. That's what the second derivative test says. Okay, so let's go ahead and do this one. And then I'll run through number 8. This one right here, we've done average cost, so I just want to kind of remind you of how you've done this. Now, I've already given you the average cost. That's because that's C bar of X. And I've given you the conditions between 1 and 5. And that's in hundreds of dollars is what it's saying there. So we're producing X units. Okay, so what production level will the average cost be a maximum? Well, really all you got to do on this one, everything's already done for you. You've already got your average cost, okay? So you're just going to do the first derivative, so that's going to be 6x to the second minus 84x, and then plus 288, like that. Okay, now what do? Set it to 0. Okay, so you're going to have 0 equals 6x squared minus 84x plus 288. Now, what would you want to do to solve this equation? What would be a good thing to do next? See if it divides by anything, because it makes it easier. It may or may not factor. Let's see if everything divides by 6. I think it does, doesn't it?
Yeah.
Which makes it nice, and it may factor. Sometimes they're just designed for factor to make it a little easier. So, yeah, let's divide everything by 6. Okay, so when you do that, you'll have 0 equals x squared. Looks like minus 14x, 48. Okay, that factors. Okay, which is good. Okay. If you don't see the factoring, you can go straight to the quadratic formula and do it that way if you want to. So this is x and x.
38 and 48.
Let's see, 8 times 6 is 48, right?
Oh, shit.
8 and 6 is 48, and 8 and 6 add up to 14. So that's how it goes, okay? Kind of interesting on this
A
problem.
real quick question.
Yeah.
So like you factored the 6 out, that automatically just drops from the problem, right?
Absolutely. See, you don't have to divide by 6. You can also factor 6 out. Then you don't have to worry about that.
Right.
Because you could divide by 6 after you factored it out.
Now, if there was an x behind that, you would have one critical number would be 0.
Right, exactly.
Okay.
Yes. Okay. So anyway, this gives x equals 8, and it gives x equals 6. Now, something about this is a little weird because it said, that this may have been something I typed wrong. That says from 1 to 5. Okay. So that's giving, and you're trying to do a production level, so 8 and 6 would be that then. So let's put this in the graphing calculator before we go to the next problem, because I'm kind of curious about that. So I'm just going to put in the average cost, which is 2x to the third. And then, let's see, minus 42x to the second, plus 288x, then plus 12. And let's do, I gave you 1 to 5. Let's go ahead and just go 0 to 10, because both of these critical points come in at 8 in between 0 and 10. And let's see, for a y value, I want to go to my table. That's what I always do, just kind of look at my table and kind of scroll through the values from 0 to 10 and see what kind of numbers. You got a bunch of negative numbers, it looks like. And somewhere in here it'll start becoming positive, I'm sure. Here we go. So it's up in the 600s. There's a 700, which is beyond that. Let's just go ahead and do like 0 to 800 or something like that. So I'm going to put in that window. I'll slide this to the side if you need to see that. So what I want to do real quick is just see if I have if those critical points look right. So it looks like we had something at 8 and we had something at 6. Well, okay, that's a little hard to see on that. So there's the 6. That kind of looks like a max. The 8, It doesn't look right at all. No, that's a minimum is what that is. Okay, so that's kind of where you get into the second derivative test a little bit. I think this had to have been wrong. Okay, so it looks like you have a max would be at x equals 6. Okay, now I want to show you how the second derivative test applies to this problem because this is a good thing to show you at this stage. So let's go ahead and do a second derivative test. Okay, so let's go ahead, and it's real easy to do the second derivative on this. So what is your second derivative? 12x minus 84. Now what you have to do is you have to plug in the 6 and you have to plug in the 8. And let me show you what happens. The graphing calculator verified something to me. But if I plug in a 6, I'm going to just do 12 times 6 minus 4. All you care about is that's a positive number. Okay, you can tell it's positive. I don't care what it is. What that means is if the second derivative is positive at 6, that means that that is a minimum. Okay.
It's 84.
Okay, what's that?
It's 12x minus 84.
Oh, it was 84. I got, okay. Yeah, that doesn't make sense because that's not what the calculator said.
Yeah.
Thank you. Okay, so yeah, that was 84. Okay, so let's do this then. Okay, that's negative now because that is actually 72 minus 84. That's a negative number. So what does that tell you?
Copy it down, which has a max.
It's a max. Okay, that's how it goes. Now plug in 8 into your second derivative. That would be 12 times 8 minus 84. That's 96 minus 84. That's positive. What does that tell you? Minimum. Does that make sense? The second derivative is kind of a slick, easy thing to do, and that's why even though 8 is a critical point, it's not a max. Okay? Sometimes that's faster to do it that way than it is the sign chart that I've been showing you. It kind of depends on the situation. Okay? Okay, any questions about these two problems on this page? Those should be pretty straightforward by now, I hope. Okay, the next one's the one that's the next two are the ones that are kind of take a while to wrap your head around, I think. This is kind of an interesting problem. And what I was working at this thing out before class, and I kind of found this is not a good problem. So I want you to change this thing where it says management determines for a $2 increase. I want you to change that to a $4 increase because the problem is a little bit more interesting that way. Now what I'm going to do, what I did on this when I was working this out, I made up an Excel spreadsheet. You don't have to know how to do an Excel spreadsheet to do this, but if you have some skill with Excel, it's actually kind of a slick way to look at this problem and make sense of it. Let me see if I can get this thing working the way I had it. Where'd everything go? Here we go. Okay. Okay, now I'm gonna put together a spreadsheet to help you do this. Just watch this, okay? If you don't know how to use spreadsheets, it's a good thing to learn how to do, okay? Because I would think that probably, in reality, if somebody was solving this problem, you could do calculus, but Excel spreadsheet would be a great way to solve this problem, okay? But I'm going to partially do this to help you understand this. So what the problem says is it says you have a hotel has 60 rooms, and if it's filled to capacity, the charge that they're charging $40 per room. Okay, so what I'm going to kind of do on this is I'm going to make like and I need to type this in. I already have this done, but I do want to kind of show you how easy it is to make up a spreadsheet for this problem. Okay, so what I'm going to do is I'm going to just label this like as this is going to be the number of rooms that are rented out. Okay, and this is going to be the cost, or I'm going to say this is like the revenue, not the revenue, but the price per room. And I'm going to kind of use this to kind of help you begin to see what the problem is saying, because this is a good thing to do to kind of help you make sense of the problem. Well, if you read the problem, here's what it says. Okay, it says if all 60 rooms are rented, then what they're doing is they're charging $40 per room. Okay, that's what it says. But then if you read on, it says, and I had you change this 2 to 4, if you have a $4 increase, then it says 5 fewer people rent. So the idea, which is logical, is the more money that you might charge for this, the less people might even come to your hotel. Okay? So what I'm going to do on this is this thing is going to, the price per room is going to change a little bit. So what it says is every time you increase the price by 4, that goes down by 5. Now here's how I do this on Excel. I just say equals, I highlight that, and then I say plus 4. Okay, what that did is that made that go up by 44. And then you can do on Excel, you can just slide this, because you're doing mathematics, you're doing algebra. What that's doing is that's just making that increase by 4 over and over again. Okay, now what the problem said is every time this goes up 4, the number of rooms goes down 5. So the way I do this in Excel is I just go equal to this number minus 5. I'm creating a formula. And then if I drag that down there, what you'll see is that's just going down, okay, like that. Does that make sense what I'm doing? The problem says when the price per room goes up 4, 5 fewer people rent out rooms. Does that make sense? Okay, now what it says is it also says that every time that you rent a room, I guess for maid service and stuff, it costs $8 to service that room. Okay. Ultimately, what you're doing is you're going to find how much should management charge to maximize profit. Okay. So these are kind of the conditions of the problem. So one of the things I'm going to do here is I'm going to find the revenue. How would you find the revenue? If it's $40 a room and you rent out 60 rooms, what do? You times them. Exactly. It's X times P, really. Okay. So that's your price and that's your X right there. So the way I do this in Excel is I say it's equal to this, and then I type in like an asterisk for times, and then I put that in. That way it does it for you automatically. So you're making $2,400. Then if I slide this down like this, okay, kind of look at your, why is it not working? Did I do something wrong? There it goes. Okay, the revenue's changing. Now what's happening to your revenue? Well, it kind of went up for a while. Okay, then it started going down. Okay, all right. Now we're going to do the cost. Okay, well, the cost was $8 per room. So what are you going to do if it's $40 per room and it costs $8 per room? How much does it cost?
40 plus
40 times 8, right? Okay, so your cost, what I'm going to do is I'm going to say this price, okay, like that. Hold on, it's the number of rooms. Okay, got the wrong thing there. Okay, so the cost is going to be equal to $8 and then times the number of rooms. Okay, so that's going to cost $480 to service those rooms, but you're bringing in $2,400. So what I'm going to do is slide that down a little bit here. And what's happening to the cost is it's going down because you're renting fewer rooms. Now what I'm going to do here is we're going to look at the profit. How do you find profit? Revenue minus cost. So what I'm going to do here is I'm going to go equals this minus this. Okay, so you're going to get a profit of $1,920 there. Now let's just see what's happening on this problem. As I go down on here, let's see, it probably is going to go up for a while, then go down. So what's happening on this, we're trying to optimize or maximizing our profit. So it looks like right in here at $48, that's where we're making the most money. Does that make sense? So see how quick I put that together? A lot of times when you're doing problems like this, you can set up a spreadsheet and solve it real fast. But also for this problem, I would hope that it helps you understand the calculus I'm going to do in a minute anyway. Okay, all right, okay. So I'm going to put that to the side and we're going to solve it with calculus now. Okay, so here's kind of the idea. Okay, first of all, what I'm going to do on this is, what we're doing is we're maximizing the profit. So when we're doing this, we know that the profit is just the revenue minus the cost. Okay, now here's where you got to be kind of careful when you're doing the revenue on this. Okay, what happened to my pen? Yeah, Excel screws up. This thing screws up sometime. Let me fix this real quick. There we go. I think we're okay. Okay, there we go. All right, so let me kind of talk about what we have here, because we're going to try to put together a function kind of like I did on the spreadsheet. So again, the profit is the revenue minus the cost, okay? And then the revenue is just really the number of rooms, and it's going to be times the cost of a room. Okay, but that's going to change, okay? The variable in those, you got two variables in that are going on, okay? So when you're putting this together, the number of rooms is always going to change as the cost of the room changes like that, okay? So we got to kind of figure out how this goes, all right? First of all, the number of rooms starts at 60, right? But then what does it do?
Decrease.
It goes down 5 each time, right? Each time the price goes up 4. So what I'm going to do here is I'm going to do this. That's going to go down, start at 60, and then it's going to go down by 5 rooms. And I'm going to put X there because what X is going to represent is it's going to be just a price increase. It's going to be the number of price increases. Now you got to think about this. The hardest part is figuring this out, okay? If X was 1, what does that mean? You've increased the price 1 time. And what do you get? 60 minus 5 is 55. If X is 2, what does that mean? You've increased the price twice, so you have 60 minus 10 is 50 and so forth. X is how many times you increase the price by $4, okay? So that's what that is. Does that make any sense? Okay? Now, the cost of the room changes. Where does the cost of the room start?
40.
40. Then what does it do?
Plus 4.
It goes up by 4.
4x.
Good, 4x. Now convince yourself of why that's right. Remember, if you do one cost increase, that's going to be $44, right? 2 cost increase is going to be $48 and so forth. That's exactly what the spreadsheet is saying. That's how it was set up. Okay, so that's the revenue, but the other thing is when we do the profit, we have to take the revenue minus the cost. So we're going to go ahead and take this expression, 600 minus 5x times 40 plus 4x, and then the cost. Okay, well, what was the cost? The cost was what? $8 per room. Okay, so you got to kind of figure that in there also. All right, so that's the number of rooms. And the number of rooms is this thing right here. Okay, that's changing. So that right there is the number of rooms. So you would have 8 times 60 minus 5x like that. Okay, so what you have is this part right here. That is your revenue coming in. And then this is the cost of the rooms. Okay, so tell me if this is making any sense. The hardest part is trying to figure this out, okay? And to me, doing that Excel spreadsheet helped me figure that out, okay? So that's what we're going to end up doing is we're going to do the derivative of this thing because that's the profit. Now, you got a couple of ways you could do this. Before you do the derivative, you could FOIL that out, multiply, collect like terms. You can do that if you want to. But you could also do this. It's easier if you do this. Isn't that a common factor? Take it out. It's less work, okay? If you don't see that, it doesn't matter. But I'm going to go ahead and take out 60 minus 5x, okay? And then when you take that out, what's left?
40 plus 4x minus 8.
There you go, 40 plus 4x minus 8. Okay, like that. Okay, now if you FOIL, you'll get the same thing. You're going to end up FOILing anyway, okay? So when we do this, we're going to have like 60 minus 5x, and then here we'll have 40 minus 8 is 32.
What, 320?
And plus 4x. Go ahead.
Isn't it 320 or 816? 40 times 8?
Well, I'm not there yet. What I'm doing is I'm subtracting.
Oh, you're
Okay, see, this is what you're left with after you factor. So I did 40 minus 8.
Oh, So you don't, all right, I was multiplying the 8.
Yeah, you're taking that factor out. Now let's go ahead and let's FOIL this. So you can go ahead and you can use your calculator on this. So let's see if we do 60 times 32, that's going to give 1920. Okay. Outside term is 240x. Inside term is 32 times 5, that's minus 160x. And then minus 20x to the second. Okay, like that. You do have like terms, so that's going to be 1920.
88.
And then that's what, 80x plus 80x minus 20x squared. Okay, so that is the profit function. All right, now we're maximizing profit, so what do we do? Now we're ready to do the calculus. Okay, I haven't done any calculus yet, so we go ahead and do the derivative, which is a nice simple derivative. That's 80 minus 40x. Okay, set that equal to 0. Now remember, when we solve this, it's going to tell you how many price increases we do. So that would just be 0 equals 80 minus 40x. That's 40x equals 80. If you move the x the other side, divide by 40, you're going to get x equals 2. So that is 2 price increases. So what does that mean? It means you start with $40, then you go to 44, then you go to 48. There's your answer, is 48. And that's what I saw on the spreadsheet when I did that, as I got that. So the optimum price is going to be, this is your optimum price, is going to end up being $48 per room. Okay? All right, now I'm going to go back to my spreadsheet here and just kind of show you what we put together here, if I can get it to open. Yeah, there it is right there. So if you look at that row right there, that showed that when you had 48, that's when your profit was at max. Okay? So those are 2 ways to approach that problem. The calculus is probably more tedious for most people than Excel spreadsheet, but those are 2 great ways to look at that problem and just show you the calculus is going to work as long as you get it set up right. Okay, does that make sense? Okay, that's a pretty cool problem, I think. I don't know about you guys, but I think it's kind of cool. Is it realistic? Probably not. Because it's never going to be that simple in the real world. Okay, I jack the price up and 5 people, less people. It's not that simple. I mean, we're at a level of a class where we have to simplify things a little bit. Okay, when things get more complicated, it gets more complicated. Okay, all right. Any questions about what I did then on that? Okay, you might want to write that down. We're talking about inventory and just kind of a control. So it's a different situation. And let me read the problem. We'll kind of talk about what it means and how you set this up. It's not really a hard problem to work out, but the setup of it you have to think through a little bit. So what this problem is saying is that the company sells 20,000 copies of a game each year. That's a condition and that's a constraint. That's a constant that isn't going to change. Okay. But then it says if you have inventory, it does cost money to store stuff typically. So it says that it costs $1 to store each game. Okay, so it's $1 a game for the whole year. If they don't sell it, they're being forced to pay in to store that in their facility or whatever. Okay, then it says each time it produces additional copies, it costs the company $6.25 to set up production. So what it's going to do, it's not going to just produce all 20,000 at the same time. It may set up production as it goes. So it might produce 5,000 of them, then sell them, and then it may do another 5,000 or whatever. That's the idea. So the question says, how many copies of the game should the company produce during each production run in order to minimize its total storage and setup costs? So the idea is, again, they're not just making 20,000 one time. They might be doing it several times. Okay, does that make sense? Okay, and the number of times that they have to run that production is what we're looking at. We're looking at how we're going to minimize that storage. Okay, all right. So the first thing is that you want to write down is what these variables are. So I'm going to kind of let you know what X is. X, we're going to let that be the let's see, how did I do that? Yeah, it's got to be the number of games in the production run. So you want to write that down as number of games in each run of production. Okay, that's what we're going to find. Maybe it's 5,000, maybe it's 1,000, and they're going to do that a certain number of times like that. Okay, then Y is going to be the number of production runs. Now this is kind of the key, is to get this down and kind of think about what this is going to mean. Okay, so before I move on this problem, let me kind of explain what's going on. I'll give you a couple of some possible answers to this problem. Okay, you don't need to write this down, but just pay attention to this. Okay, let me ask you and see if you guys understand this or not. Let's say that every time they produce, if they produce 5,000 games, how many times would they have to produce 5,000 games? How many times? 4, right? How come? Because that would be 20,000 games. That's a fixed thing, 20,000. Another possibility would be 2,000. Every time they produce, it's 2,000. How many runs would it take to make 20,000 then? That'd be 10 runs. Okay, that's the idea. Those are possible answers to the problem. 10 runs, they make 2,000 games each time. 4 runs, 5,000. They could do 1,000 games and then produce 20 times. Does that make sense? Okay, that's important in the problem to get your head around what that is, because we got to start putting together equations then. Okay, so what we're going to do then is, now what we need to look at is the cost. So next thing we're going to look at is the total setup cost. Okay, and you got to read the problem to kind of see what that's telling you. So your total setup cost, okay, what it said in the problem is, it said every time that you produce, it costs $625. Okay, so the idea would be on this, like if you did 4 times, made 4 production runs, then that would be 4 times 625, right? Okay, if they did 10 production runs, then it would be 10 times 625. So the idea is, this would be, in general, this would be 625 times y, because y is the number of production runs. So that's 625y. Okay, does that make sense? Every time they produce, it costs 625. So if they produce 10 times, it would be 625 times 10, and so forth. Okay, so we got that. Now the next thing that we have on this is the total storage cost. And you got to kind of work with an average here, total storage cost. Okay, so what the problem says on this is, it's saying it's $1 per game. Okay, every time that if it's stored, it's going to cost $1 until they get rid of it and it's pushed out of the inventory. Okay, now this diagram, I'm going to kind of show you what this average is, because what you're doing on this is you're working with an average. So what's going to happen, and see if this makes sense to you. So let's say, for instance, they do the first production. Well, what's going to happen on this is the number of video games is going to go down because they're selling it, right? Then they run out, and then they go to the second production. Then they have some more games, and then they keep selling them, and it run out. Then they produce again, and so forth, right? That's what's happening. That's what that diagram is representing. Well, the average is what we're going to work with. So the average of x is just half of that, x over 2. So we're going to use that number there kind of in half, and we're going to use that. Okay, so what this is going to be is, it's going to be $1 times, and it's the number of, now see, x is the number of games, so we're going to use that average on that. Okay, and the reason we're doing that average is because we want to we got to find out how many games it is anyway. We got to find out in each production run how many we do. So we're just going to take the halfway point from the beginning until they've sold everything. So we're going to do that. So that actually is going to end up being 1/2. 1 over 2 is 1/2, so that's just going to be 1/2 x. And let's go ahead and just write that as 0.5x. So that's the total storage cost as you get that then. Okay. Now the average is just the halfway point. It would be kind of like this. If you produced 5,000 computer games, then you would look at the halfway point is the way we're going to base that on, which would be 2,500 games. Okay. Then what we're going to do is kind of get together a total cost. And this is going to be the total cost that we're going to work with the calculus on. So what it's going to be is, it's going to be the setup cost. We've got 2 costs. We have the setup cost, and then we have the storage cost. Okay. So we've already got those 2 things. So we found that the setup cost was $625. Okay, so we got that 625y. We figured that out. And then we got the storage cost based on the average was 0.5x like that. So this is what your cost is. That's what you're going to end up working with the calculus on. Okay, this is the one that's a little bit harder, I think, to understand. What this says, remember, what is y? Y is how many times they produce. Okay, so if you produce your games 10 times, then 10 times 625 is how much it costs to start up the production. And what this is saying is x is how many games you're producing. Okay, so what we're doing on that is we're basing that on the average because we're doing different runs on that. That's the reason we're doing that. So that's what we're going to do a derivative of. The problem with this is how many variables does it have? It has 2. What do you have to do? Only have 1 variable, okay? So the other place where this comes into play is this right here is what you're going to differentiate, but the other thing comes from here. Okay, so it turns out on here, if you just take x times y, you're going to get a certain number. What is x? X is the number of games. This is the number of runs. So like, what did you do? When you did 5,000 times 4 and 2,000 times 10, what do you always get? 20,000. So that is your equation that you're going to use to turn this into a function of 1 variable. Okay, that's what this problem is saying is, and again, just to kind of help you remember this, let's just say, for instance, that you did 4,000 games. Well, how many production runs would it take to get 20? It'd take 5. Okay, that's how x and y relate to each other. They multiply to give 20,000. So what we're going to do is let's go ahead and take this equation and let's solve it for y. You could also solve it for x. It doesn't make any difference. Now we're going to take that, and what are you going to do with this? You're going to plug it in there. Okay, because before you do your derivative, your function's got to have 1 unknown in it. Okay, once we get past this point, we've done, in my opinion, the hardest part of the problem. So what we're going to have is c of x is equal to 625. Replace the y with this. Okay, 20,000 over x. Then you have the plus 0.5x like that. Now that's what you're going to take a derivative of, set equal to 0, and then you're going to minimize. You're looking for a minimum on that. Okay? All right, so let's think about how we would differentiate this. Okay, what I'm going to do is I'm just going to take, on my calculator, I'll take 625 times 20,000. You'll get a real big number. So that's going to be 12,500,000. Now, instead of using a quotient rule, just bring that to the top and make it x to the negative 1, so you can use a power rule. And then leave alone the 0.5x like that. Okay, so we've got everything put together now. Okay, do you guys kind of follow what I'm doing, okay? All right, this is kind of tricky to wrap your head around, I think, particularly that average cost in there. Okay, go ahead and do your derivative. Okay, so when we do that, it's just a power rule. So you'll bring the negative 1 down, multiplied by the constant, and then the exponent goes down 1 to negative 2. And the derivative of 0.5x is what? 0.5. So there's what you have. Now you're going to set that equal to 0 and solve the equation, and this will give you x, and then we'll find y, and then we'll try to see if we can make sense of this problem. Okay, so what I'm going to do is go ahead and set it equal to 0. This is 12,500,000 all over x squared plus 0.5. Okay, how are you going to solve an equation like that? Get x on one side, right? Okay, the best way is just to move this over like that. So if you do that, you would have positive 12,500,000 all over x squared equals 0.5. Okay, now you can cross multiply this one if you want to. A simple way to do this is just put that over 1. It's a proportion, so you can cross multiply. So if you do that, you would have 0.5x squared is equal to 12,500,000. Okay, so we got that. Then what?
Divide by 0.5.
Divide by 0.5, then what?
Square.
Square root. Okay, good. Okay. So you're going to divide that by 0.5. When you divide by 0.5, it actually doubles the number. So that'll probably give you 25. You can verify on your calculator if you want to. I'm pretty sure it's 25 million. because that's what, dividing by 0.5. 0.5 is a half. You divide by a half, you double, okay? Then we square root. That's probably 5,000. Yeah, that's right. So that would be x equals 5,000. The problem's kind of designed so it was a nice number, okay? Now, go back to the problem and let's kind of look at what x was. In this problem, x was the number of games that you produce in a run. So what does that mean? It means every time that you produce, you're going to make 5,000 games. They're all going to sell out. Then what are you going to do? You're going to turn around and make 5,000 again. How many times do you have to produce that 5,000? 4 times. Good. Okay, because see, that's where this comes into play. Y is going to be 20,000 divided by that 5,000. So you're going to get 4 runs.
So real quick, the reason why you're doing it in runs is to avoid the storage cost?
Yes, exactly. Yeah, see, the thing about that is using these conditions of the problem is that kind of minimizes those. You got the conditions of the storage cost that come into play, and then, of course, the production costs money. So you wouldn't want to do, like, produce 10 video games every day because it costs you $625 each time you produce, just as a startup cost.
So we're basically factoring both those.
Exactly.
The storage and the amount.
Right, exactly. So you got the setup cost, $625Y, then the storage cost. Okay, was 0.5x. So that's the answer. It would be like 4 runs, and then it would be 5,000 games like that. That's the answer to the problem. Okay, it's kind of an interesting problem. I haven't seen that before in teaching this class before. They have this in the book, so I think it's kind of a different kind of problem to look at. It's kind of interesting.